So we finished up last time talking about switching over into these repeated measures designs and talking about some of the strengths conceptually with the repeated measures analyses. Can someone tell me, so why might we, if we have an opportunity, want to use repeated measures analyses for different studies, research stuff that we're working with? What's the main advantage of this? Yeah. Power. Yeah. What we're doing is all of us individually, any participants you're going to have come in, they're going to differ for reasons that aren't in your model, right? There's no way to capture all the reasons. Josiah is different than Emily, that's different than Sam, so on and so forth, right? But if we go through and start to measure the same people across repeated assessments, what we can start to do is start to parcel out those things that make Josiah unique, that make Amanda unique in terms of how they respond to certain things. And what happens is we can start to model that individual different stuff and kind of put it somewhere else, right? But when we take that out of our big error bubble and move it somewhere else, what it does is it shrinks down that error in that model, at least for the effects that we're looking to test. And if that error term is smaller, it just gives us a clearer picture. Think about error as static, right? Old school, like turning in a radio dial, right? I'm trying to get a signal. I can kind of hear, but there's a lot of static, makes it tough to be real clear about what's going on. If we can dial that back, we can start to get more powerful estimates of what's going on in our data. So again, what we're going to be doing with these repeated measures and other designs is we're going to just have one sample of individuals that we're going to go through and we're going to measure them on multiple occasions. And because of this, what we can do is we can go through and start to model out the correlation between our repeated assessments, which starts to become advantageous for statistical and interpretive purposes. In general, we want our individuals in our studies to be independent. If they're not in a design that doesn't account for that, then that's a problem. With our repeated measures designs, we know that we're going to see correlated responses. We can model that, and then we get, oh, let me get it. The advantage is that. All right. So let's take a look at and think about sort of this small table here. Okay. If we're looking at this table right here, if we're looking across scores within treatments here, A, B, and C, let's think about these as if they were just independent conditions. If we're doing like a regular old one-way ANOVA model where we've got condition A, B, and C, okay? Amanda, how much variability are we seeing within scores in condition A, condition B, and condition C?
The bottoms are the means, right? So
Bottoms are the means, yeah. We're looking at sort of within condition variability.
so areas.
Yeah.
Are you asking this?
Just in general, how much are you seeing a lot of variability in these scores? Yeah, a good amount of variability in here, right? Remember that for a between subjects design, like a regular one-way ANOVA, we're assuming that whatever our condition is accounting for variability in whatever we're looking at. And so essentially everybody within, if I model all the variability in my outcome, or my grouping factor is the only thing that determines the outcome, then everybody within the same condition should have the same score. Here we don't have a lot of variability or a lot of consistency, right? We're kind of all over the place, right? So we've got a huge amount of variability within each one of these conditions. And what about variability across the conditions? If we're looking at the means at the bottom, Basha, are we seeing a lot of differences in the means across the bottom? To some extent, but is it more than sort of the differences that we're seeing within the conditions? No, right? So for between subjects design, not a problem because we've got a lot of within subjects, within condition variability, which is our error, and not that much between subjects or between condition variability, which is our effect, which means that we're probably not going to find much of anything. So again, this would not be advantageous if we were to go through, and these were the data that we were seeing in a straight one-way ANOVA design. But if we look at sort of what's going on here, we start to see that a lot of the, if I'm looking across these lines, what's going on, Matt, if we're looking just this way across these lines, if we're looking from 4, sort of this, let's say this line from 2 to 4 to 7, 10 to 12 to 13, 22, 29, 30, what's happening here?
Well, the numbers are going up generally.
Yeah, so we're seeing pretty consistently things are increasing. Are they increasing by similar amounts?
Not always.
Not always, but to some degree, right? Sort of kind of increasing across incremental assessments, right? So here we've got something that's going to for sure come up with null effects. But if we look at these data as if they were modeled within subjects design, right? Here we've got participant 1 starting out at his level 2, then they go to 4, then they go to 7, right? So they're increasing. 2 starts at 10 and jumps up 12, 13. Here 4 starts at 30, 31, 34. So here we're seeing a whole lot of garbage and mess and sort of not much going on. But if we look at this and actually look, even though people are starting at different levels, subject 1 started at a score of 2, subject 4 started at a score of 30, huge differences. If these are actually representing a repeated assessment where it's just these 4 people assessed at 3 different time points, we're starting to see a much more orderly pattern of data, even though everybody's starting out at different places. Everybody's has that individual difference. Everything's moving kind of in a systematic increasing fashion across these assessments, right? And so what we see that even though we've got a lot of within condition variability or within time point variability across individuals, within individuals, we're seeing very systematic increases here, right? And so what we've got is a treatment effect that's consistent and reliable with everybody increasing across steps. Now, all of a sudden, if we can say, just focus on that piece, we've got a much more powerful design, okay? And so what we see with our repeated measures design, we're reducing this error by taking out the individual different stuff, okay? We're just taking all the reasons why 1 is different than 2 is different than 3 is different than 4. We're taking that, modeling that out as between person differences, and just looking at variability that's related to this the interdependence across repeated time points. What this does is it reduces the noise that we're getting in this, and if we have less noise in our model, it means we've got more power to detect our effects. Do we necessarily in this model, Rachel, do we care about the way we have this set up? Do we necessarily care about why 2 is different than 3? No, right? If we did, we probably would have modeled something in there. What we're more concerned about is, as a whole, how are people changing over the course of repeated assessments? And if we're only focused on that, we can take that other stuff and say, I don't know why it's there, but it's not relevant to what we're doing. We're just focusing on this. People kind of understand conceptually what's going on and why these start to be incredibly powerful designs. Okay. So for our one-way repeated measures ANOVA, okay. Our simplest repeated measures ANOVA design, we're simply asking, do scores vary across repeated assessment of some variable X, right? Our null hypothesis here is that the mean of repeated measure 1 is equal to the mean of repeated measure 2, so on and so forth. Okay. And what we're going to do in these analyses is we're going to start to, if you remember back to our ANOVA, the whole design is about partialing out different components of variability so we can start to detect the effects that we're interested in here. Same thing with our repeat measures designs. It's just going to look a little bit different. What we're going to do is we're going to start with our sum of squares total. Someone tell me, can you tell me what a sum of squares is?
It's when you square your standard deviation.
Close-ish. So we're summing our squared deviation scores, right, from the mean, but conceptually, what does a sum of squares represent?
Something below the mean. It's something, because standard deviation
Yeah,
has to do with how far away a score is from
Yeah.
the mean. So,
so
the population maybe for,
not necessarily the population. So if I say, hey, I've got a measure of sum of squares and a measure of variance and a measure of standard deviation, are those different things?
Yes.
They are different things, but they're all kind of measuring the same concept, right? Variability. Sum of squares, variance, not super interpretive, don't have a lot of interpretive value, just interpretive face, but it's all different metrics of variability, right? And so when we're talking about our sum of squares total, here we're just talking about all the variability in our data, okay? And again, this is going to be in terms of squared deviations from the grand mean. So if we look at our sum of squares total here, conceptually what we're doing is we're just taking every individual score, subtracting it from the grand mean, and just squaring those and adding them up, right? So we've got 2 minus 18.76 squared plus 10 minus 18.7 squared, 76 squared plus 22 minus 18.76 squared, so on and so forth for all scores in the data. This is giving us the total variability in our set, right? This is our total piece of the pie. Okay. But then what we're going to do is we're going to take that sum of squares total and we're going to separate it into the stuff that's due to individual differences, the between subject stuff, and we're going to separate this stuff out to look at the within subject stuff. Okay, our between subjects, our sum of squares between, we're going to take the mean of our participant scores across assessments, and we're going to subtract that from the grand mean and square those up. Okay, what this is looking at and what this is capturing is collapsing across assessment points, just taking the average for each person in our set. To what extent do people differ from the grand mean, right? If there was no differences across people, then these are all going to be the same, and there's no variability across individuals, and so then we've got no between subjects variability. We've got clones replicas of one another, but that's never what's going to happen, right? We're going to have reasons. So 1 scores systematically lower than 3, and 2 scores systematically lower than 4. 4 is bigger than everybody for reasons we don't know why, but we're just going to take that and we're going to partial it out. That's the stuff that we're going to say is just due to individual differences, okay? And we're going to take that. So we're going to take the participant mean, subtract it from the grand mean, square that, add it up, multiply it by the number of assessment points that we have, and we're going to take that and we're going to pull that out of the total. We're going to set that to the side, okay? Now our repeated measures sum of squares, this is going to be the mean of our repeated measure minus the grand mean. So here what we're going to do is we're going to take 16 minus 18.76 squared plus 19 minus 18.76 squared plus 21 minus 18.76 squared. If we look at what we're doing, this is getting captured in our repeated measures, sum of squares for our repeated measures. This is our effect. This is the systematic change of repeated assessments, sort of in terms of the deviation from the grand mean from sort of everything going on here. Okay, so what we've done is we've taken our sum of squares total and we've separated it into between subject stuff and within subject stuff. Okay, and then what we're going to do is we're going to leave the between subject stuff alone. That's error. We just kick that out. We don't care about that. That's not relevant to our analysis. But then what we're going to do is we're going to take our within subjects sum of squares, and we're going to separate that into stuff that's specifically related to our effect of interest, and separate that from just random error stuff that's going on here. So if we take the sum of squares error, we get this by subtraction. If we take the total and subtract the between and subtract my repeated measures, excuse me, this repeated measures here, what is left over is my error. Then I can work backwards through arithmetic and get this sum of squares within. Okay, so misspoke here. What we've got to do at the total, calculate the between. That's error that we don't care about, right? That's just due to because people are different than other people. What we then do is we can calculate our repeated measures. This is our actual effect that we're looking at here. and anything that's not associated with the between subjects sum of squares and the within the repeated measures sum of squares, everything else that's left over is just our error term here. Okay, and if we add a repeated measure error or repeated measure sum of squares, or excuse me, sum of squares repeated measure or sum of squares error, that's going to give us this sort of computational within subjects variability piece that we then break out. Okay. Questions about where these different variance components, how we're getting them, and what they mean. Yeah, Emily.
I really love that. With definition question, what is the K variable stand for?
Yeah, I'm sorry. K is just the number of repeated assessments.
Cool.
So in this, it's just going to be 4. Other questions? All right. So what we should always think about with our sum of squares, always think about first taking our sum of squares total, partitioning it into the between stuff, and within kind of separating that out. And again, the reason we're calculating that sum of squares between is to sort of absorb that correlation, to account for the systematic association for Y2 or across repeated assessments. One score is related to their first score, related to second score, related to the third score. That starts to go through, pull this out. We remove this from the error term, and it starts to create very, very, very powerful designs that are great for theses and dissertations and other things that you really want to turn out. This is a nice design. All right, some assumptions of our repeated measures. For our one-way repeated measures ANOVA, it's pretty straightforward for the most part, and it will be things that you'll be familiar with. We generally feel, or sort of people will often interpret repeated measures ANOVAs similar to our other means-based analyses, suggesting that these are pretty robust. You can have some stuff going on with your sample and cell size is reasonably okay. Could be approximating reasonable estimates. I mean, there's controversy around this, but generally you can assume that these tend to be pretty robust analyses. Remember that our normality assumption here involves normality in the distribution of sample means. Okay? Can someone tell me what normality in the distribution of sample means? Sorry.
That just means when you take all the samples, averages out each pair of samples, and then you take this. That has to be normal.
Okay, perfect. Yeah. So what we're talking, so Josiah, do we have assumptions about specific distribution of the scores that we're looking at in our data set? No, right? Technically we don't, right? So the assumption is not that the data that I'm looking at is necessarily normal, although it's nice if it is. My main concern is that is the distribution of sample means for this sample given the size of the sample that I've collected, is the distribution of sample means normal, right? And so the distribution of sample means, remember, is if I were to collect all possible samples of size X from a population, and I were to take the mean of those samples, would the mean of each of that infinite number of sample means, would that create a normal distribution, right? And here we're talking about central limit theorem. Under what two conditions do we see the distribution of sample means approximate normality very quickly? Yeah.
Over 30, and over 30.
Okay.
Well, a large sample size.
The larger sample, okay. I worry about sort of like, oh, it's 29, it's not 30, it is. Not really so much like that. But yes, as our samples start to get larger, even if we've got scores that are very, very skewed, very, very not normal, distribution of sample means is still going to approach normality pretty quickly, so long as we have reasonable representation of ourselves. And this starts to become important, right? When we're thinking about experimental folks, where you're doing more like lab-based, maybe lab-based studies and things along those lines, right? Old school stuff, that, oh, I got a cell size of like 8 or 10 or something along those lines. Start to worry about are these things gonna, is the distribution of samples of a cell that size gonna approximate normality? There's a lot of problems with that, right? Now, if you're running samples, experiments with cell size 30, that's a pretty decent sized cell, right? But kind of around that area is where we start to think, like, yeah, I probably have a little bit more wiggle room with this, right? So thinking about that. So if my cells or my conditions are relatively large-ish, and I would call 30 a large number, but within this context, it's sort of getting around that. Even if the actual scores I'm seeing are looking kind of funky in terms of skew and stuff like that, I'm probably not going to be too worried about that because the assumption isn't about the actual distribution of my data, it's about the distribution of sample. Okay. What's the other situation in which distribution of sample starts to approach normality pretty quickly?
Yeah, I think it was like the population.
Yeah, if whatever I'm measuring is normal in the population, then it's going to be like, if I'm measuring, say, height, right, and my particular sample of, say, 25 doesn't look super normal, so the observed score is a little bit funky. I still know that height has a normal distribution in the population, so I'm probably not too concerned about that, right? So these are the things, same thing with our ANOVA models. This is the concern, the distributional concern. We're still going to go through and look at our distributions just so we can sort of detect if anything weird is going on, or if there's strange outliers, or just screening tells us a lot about our data and our method and sort of what's going on there. But we're not going to be too worried about if things are way off base here. Okay. Where we will start to worry if we have obvious violations of normality in our observed data, if I have different shape and different variance, right? If I've got on this, if I've got one situation, I measure everybody at one time point, and I got like a crazy positive skew with massive variability, and then I measure people at the second time point, and I've got an opposite skew, but very little variability at all. That starts to wreak havoc on stuff. That's not good. If I have unequal variance and unequal sample size here, this shouldn't be too much of an issue, because if you don't have the same number of observations, that person can't be included, because everybody needs to be on the same assessment repeatedly. There's some stuff we can do, but in general, if we're not imputing scores or using a different model, you're going to have the same number of people in each repeated assessment. Also, violations of normality in small sample size. If I've got cells of 10 to 12, and I've got crazy skewed distributions with people with huge, massive scores hanging out on the end, what's my main concern there? Why do I start to become increasingly concerned about extreme scores if I've got small samples? That's going to start dragging my means all over the place, right? If I've got one person hanging out there, now if I've got a big sample, I expect to have extreme scores, right? But if I've got a sample of 80, like one person hanging out, it probably isn't going to drag that out too much. But if I got 10 or 12, it can start throwing things over. Yeah.
In terms of the unequal sample sizes, like, I know you don't like having labels for when to cut something off or how to dichotomize things, but what's like an estimate so we can know if something is like super unequal?
Just to sort of look at the ratio. I mean, like sort of some things, well, the rules of something like say 3-to-1, which is pretty extreme, right? This is something that people sometimes will get worked up about. Like, oh, I randomized my participants to condition, but I've got 25 people in this group and 30 people in that group. My randomization failed. We're expecting them all to be identical in terms of numbers. How that works. I mean, at large enough samples that will happen, but that's not such a huge deal. But if you've got orders of magnitude difference, right, and sort of where this can come up sometimes, if I'm looking at trying to look at like diversity issues and sort of stuff in a place like Wyoming, right, where I have 90% of my participants or 80% of my participants reporting as white non-identifying as white non-Hispanic, and I've got a handful of people who identify with sort of other sort of cultural identities and stuff. And then you've got like a huge, massive imbalance, and then it starts to become questionable about physically, is this something that I can compare to get something meaningful out of, right? So this is the type of stuff. Generally, this isn't a thing when we're working on standard, like lab-based studies, because you're not gonna accidentally put 90% of people into one condition and 10% in another. But for naturalistic stuff, it's something that should sort of get you thinking about where we're going with this. All right. Questions about our normality assumptions. Okay. Other assumption that we have here is going to be our homogeneity of variance across individuals or across intervals. So here we're assuming that the variability at time 1 is equal to the variability at time 2 is equal to the variability at time 3. We're assuming that we're not getting very little variability at the first assessment point and massive variability at the last assessment point, although this is something that we need to be thinking about. Generally thinking about testing this in day-to-day life with our Fmax statistic. Fmax, we're just taking our largest variability over our smallest variability, creating a ratio, or our largest variance over our smallest variance, creating a ratio of that, like anything that's around 5. This is sort of at least reasonably close-ish. We generally think about our ANOVA designs as being pretty robust and simple violations of homogeneity. Now, if I've got wildly different sample sizes, which can't really happen in a one-way, but we start to get into mixed factor ANOVA, where we've got between and within factors, then that can start to come. So questions about these assumptions. All right. We also have something when we go through and transition into our repeated measures designs, we're also going to have assumptions about our variance covariance matrix. Okay. So in the background mathematics of running these analyses, what's going to be going on, we're going to be looking and pulling information from the variance covariance matrix of scores from our repeated measures. Okay. Here's an example of what this might look like. Essentially, I have A is assessment time, assessment 1, B is assessment 2, C is assessment 3. If I were to go through and to put together, think of this as like a correlation matrix, except for instead of standard values covariances, we're talking about just regular covariances. So in the diagonal here, this is the variance of measurement at assessment 1. This is the variance of assessment at measure 2, or this is the variance of scores at assessment 2. This is the variance of scores at assessment 3. Okay, and then the off diagonal, we have covariance. Someone tell me what covariance is. Yeah. Perfect, right? It's just the extent that if sort of this moves, the other one moves in concert with it, right? And if we go and standardize that covariance, that's where we get our Pearson correlation, right? So basically what we have here is just a raw metric of variance and covariance sort of within this. Okay? Now what we assume here, so there's a couple of different things that start to become relevant. And so terms you're going to want to be aware of. If we're talking about a variance matrix that demonstrates compound symmetry, this is going to be a situation where your variances and your covariances are all identical within the population. So basically what you would say, if this matrix evidence compound symmetry, you would see your variance at assessment at time A, variance of scores at assessment B, variance of scores at assessment C, were all identical. Also, the covariance or the relation of the association in these off diagonals would also be all identical. Okay? So basically we're saying if the variance was 150, we see that the variance at the first assessment was exactly 150, at B, almost exactly 150, C, almost exactly 150. Covariance, if it was 160, it would be 160 sort of between A and B, A and C, B and C, all the same thing. Yeah.
So is that essentially our null?
What's that?
Is that essentially our null hypothesis?
It's not exactly a null. It's just saying that you have perfect symmetry within sort of this within this thing, and basically like if your standard deviation across all assessment points was identical and all your assessments correlated equally with one another, that would be an example of compound symmetry.
So it's within your sample.
Yeah,
Okay.
right. Well, I mean, it's assuming that this is going on in the population, but you would see something where everything will look pretty similar within your sample.
Okay.
Okay. But this is overly restrictive and not necessary for our repeated measures. For our repeated measures ANOVA, what we're concerned about is characteristic known as sphericity. Okay. Sphericity exists when we've got the difference score. If you look at the difference scores for each pair of our repeated measure have equal population points. Okay. So this is saying if I took everybody's scores at time 1 and time 2 and created a deviation score and looked at the variance of that deviation score, that variance would be the same as if I took the difference in people's scores from time 1 and time 3 and looked at the difference between that, and that had the same variance. And if I looked at the difference in the people's scores from times 2 and times 3, looked at that difference, looked at the variance there, the difference in those, the variance in those deviation scores would be the same. If this is the case, what we would say is that we have achieved sphericity in these data. And if we've achieved sphericity in our across our repeated assessments, what this means is that our F test that we're going to use is all they're going to be good. The F test that we calculate, the distribution of the F test that we calculate is going to follow a distribution of the F test that we're using to test the thing. It's not some other weird distribution that we don't know about. But as we start to violate this assumption of sphericity, we start to get F ratios that won't follow the distribution that we think it should. And then our inferences are all thrown off base. Again, this is always the problem when we have violations of our assumptions. Remember that our statistic models were built in a mathematical vacuum, right? Under these conditions, our test statistics, sampling distribution of our test statistics will follow this. And so with that, we can say, assuming that the null hypothesis is true, how likely is it for me to get it to the test of 3 or 5 sort of versus something else, right? But as soon as we start to violate those assumptions, now all of a sudden we're still calculating our test statistic, or the test statistic has some distribution that doesn't map onto the one that we think it does, and we start to lose precision in terms of our inference with things. Yeah.
Sorry, I'm kind of confused. What's the difference between compound symmetry?
Yeah. So here we're saying that the variances are all identical with one another.
For compound symmetry.
For compound symmetry.
Okay.
Sphericity is just saying if I take my assessments, my first assessment, and I subtract it from my second assessment, the variance of those different scores is the same as if I take the first assessment and the last assessment, subtract those scores. That variance is going to be the same as if I take the second, subtract the third. Look at the difference in those. And so essentially what we have is if I have a variance covariance that meets criteria for compound symmetry, it's also going to meet for sphericity. But I can have a variance covariance matrix that meets for sphericity but doesn't demonstrate compound symmetry. Okay. So compound symmetry is not a requirement for valid tests of your repeated measure to ANOVA, but sphericity is. Okay. So sphericity is a less restrictive form. The reason I'm sort of putting this together, sometimes people will misunderstand what this needs to happen, and they'll confuse compound symmetry with sphericity and look at their correlate or the standardized version of this correlation matrix that go, well, my correlations are different, so therefore I have a violation. Probably, but that's not technically the assumption going on. So people kind of understand what we're at least kind of have a headspace for what this variance covariance assumption is within our. The good news is you won't have to worry about it when you default to correction. You won't have to concern yourself with it too much, but I want you to know kind of what's going on and why we go through. All right, so why is sphericity a problem with this, okay? Sphericity, so even though we're introducing it as an assumption of our repeated measures design, it's an assumption of our between measures design as well, okay? The issue is, if I have a between measures design, I assume that there is no correlation in scores between condition 1 and condition 2, condition 3, so on and so forth, because they're all different people. And so I assume all the intercorrelations are going to be 0 anyway, and so I don't really worry about it. So long as I don't violate my independence assumption, I don't worry about sphericity, because everybody's independent of one another and everything should have 0 correlation anyway. So it's not technically a new assumption, it's an assumption that's already been there. We just haven't talked about it because sort of the overarching assumption is in a between subjects design is that everybody's scores are independent of one another, so you won't have to worry about it. Okay. But when we transition over into our repeated measures ANOVA, we expect our scores not to be uncorrelated. In fact, we're really banking on them to be correlated. That's what gives us confers power in this design. And so what we're assuming is that those correlations are some non-zero value. Before in our between, we just assume they're all 0 and we're good. Here, we do have correlations, and so now we have to start worrying about kind of what those associations are and the extent to which they're equivalent to one another, right? In the research that we do, this sphericity assumption is almost never tenable, okay? Like this is one of these assumptions, we just assume that we violated it all the time. And a lot of this just has to do with how we as three-dimensional humans move through space and stuff, okay? As I go through, and I have a group of individuals that I measure, let's say I measured you, say, looped all of you into an EMA design, and I'm having you report your mood every half hour. If I were to look at the relation, the association between those assessments, I would expect that assessments that are collected closer in time are going to be more highly correlated than measurements that are farther apart in time. And this is almost always what we see, right? So if I have a developmental study and I'm measuring something that should change, I'm expecting sort of here and here to be more close in, these two be more closely related, these two be more closely related than this and this. Just as a function of the design, we're sort of almost certain to build in violations of sphericity. Okay, and so because of this, we have to be thinking about how do we go through and address this. So the repeated measure design, the math on the repeated measures, I know that's great, except when we actually try and do something with it, and then it doesn't ever work out just because things closer in time, more with greater temporal relation to one another, tend to be more correlated with one another as opposed to things stretched out. So for these designs, the assumption is always that you're going to violate sphericity, and so you're automatically going to go to some correction that goes to and accounts for the fact that we violate the underlying assumptions of mathematics, so we need to make some correction. Questions about this? People see kind of why this is a problem and why we just fall to assume that we've violated, made a violation of this. So our corrections that we can make. This used to be kind of a bigger issue. It's not a bigger issue because now this is all just kind of become standard for the field. But when you go through, you look at your output, you'll get a number of different corrections that you could use. We're going to talk about those just so you know what this is about. We can in SPSS request a Mauchly test, and what this is a statistical test to test for deviations of sphericity, right? So basically, it's kind of like your homogeneity variance test. It's just testing whether or not you violate the sphericity. Problem is, it's underpowered. If your data are not normal, it's sensitive to that. And so what we're going to do is we're just going to assume that we violate the sphericity and go straight to our corrected statistics. Okay. Now, what we're doing, the same thing as when we were talking about our independent sample tests, right? Emily, let's say I have evidence, I have evidence for a violation of homogeneity parity, right? So what do I do then when I'm looking at my SPSS output?
Well, that's one way.
What's that now?
I can't remember what it's called.
And there's a line on there that
Yeah.
says that we've had a violation of
Yeah.
homogeneity, and so equal variance is not assumed when you
Yeah.
go through and do this, right? Remember that for that test, what the Barron's Fisher, what said, yeah, that's what it is, that correction. It's assuming that test that we calculated does follow a t-distribution. It's just not a t-distribution with degrees of freedom that we would expect it to, because we have a violation of homogeneity, right? We assume that sample distribution at test is still going to follow a t distribution, but remember t is a family distributions, and so what we do there with when we're looking at that is we're comparing that test statistic against a t distribution that has some degree of freedom different than what we would normally test against if we didn't have a violation. Same thing with this, right? What we're seeing with these violations of sphericity, what we're seeing is we're seeing an adjustment in the degrees of freedom, okay? So if I have, Matt, what's the advantage if I'm in my t-test, if I have a t-test with 150 degrees of freedom and a t-test with 30 degrees of freedom, what's the difference between that? Like why would I prefer one over the other?
I know the higher degrees of freedom means you have larger samples, so that's one reason you get more power to be able to identify an effect. I don't think that's the answer you're looking for.
What happens in my benchmarks for my critical value to claim for interpretation as my degrees of freedom increase? If we're thinking about that distribution, and here are my goalposts, right? As my degrees of freedom increase, what happens to my goalposts? They move in or out?
So let's see. So as the sample size increases, the distribution narrower.
Yeah, right. I get more precise, right? Because remember, our t-distribution is just a correction to z, right? Because we know we're going to underestimate our, with small samples, we're always going to underestimate the sample variance. If our sample variance is too small, what happens to our standard error? If I underestimate my sample variance, what happens to the standard error of my test? Standard error goes down, right? Because my variance, my standard error is just my variance over the square root of my sample size, right? If I underestimate my sample variance, I've got a smaller number in the numerator, and so it's going to go down. If my standard error is too small, what happens to my test statistic? Goes up. We're on opposite, right? So if I underestimate the sample variance, I'm sort of the thing that goes in the numerator of my standard error is too small. So it makes my standard error too small, which makes it seem like I got a more much precise estimate than I do. And the standard error goes in the denominator of my test statistic. And so if I plug a smaller number into my denominator, it makes my test statistic go up. And so what I would essentially do if I were to just run t-tests and just compare against critical values for my z table, I reject it no more than I should. Right? And that's why we have a t-distribution. Remember, a t-distribution is a family of distributions. As the degrees of freedom go up, it gets closer and closer to z, and so it asymptotically approaches a z distribution. So if I have a sample with 15 degrees of freedom, the test statistic that I need to achieve in order to claim evidence for an effect needs to be bigger than if I have something with, say, 500 people or 500 degrees of freedom. Then I'm essentially working with the z distribution. Okay, so same thing with this is what we do because we assume a violation of homogeneity variance. What we're going to do is these corrections are going to involve an adjustment of the degrees of freedom for your F test. Okay, and what it's going to do is it's going to decrease your degrees of freedom relative to what computation you should get. Then my degrees of freedom decrease, Sam, what happens to the critical value that I would to achieve or claim that benchmark from that effect? It gets bigger, right? So what we're doing is we're getting a penalty for violations of homogeneity variance. Okay, so what we do, is that tiny, is that epsilon? Is that really?
Yeah.
Is that what that is? Okay. Epsilon equals 1, assumes my severity assumption is met, right? If I have an estimate of epsilon 1, I'm good to go. My value of epsilon decreases as the violation of my violation of severity become increasingly more severe. So what we've got is different corrections that are made in an adjustment based on your estimate of epsilon here. Okay, and don't worry, you don't have to worry about any of this stuff with the program. You see a couple of corrections. Your greenhouse geyser, this is going to be your one that you'll probably, unless you've got like sort of a really compelling reason not to, which is probably going to be hard to level here. But basically, your greenhouse geyser correction is going to give you adjustment on your degrees of freedom based on the greenhouse geyser variation of epsilon. We call that epsilon hat here. Okay, and so what this correction is going to do, it's going to measure epsilon, which is your measure of sort of the extent to which you violate sphericity. And based on that estimate, it's going to make an adjustment for degrees of freedom to give you something that should be it's going to be a more conservative estimate for your effect. Okay. We also have a correction, a Bloom-Belt correction, based on an alternative estimate for epsilon. For cases where the true value of epsilon is greater than 0.75, right? So if you don't have a massive violation of sphericity, Bloom-Belt is saying like, oh, hey, we're just going to do a slightly less stringent correction for this. Assigns less penalty than greenhouse geyser. But one, Powell notes that the Bloom-Belt correction in SPSS and SAS is not correct. I haven't checked this. Maybe they, I don't know. SPSS, I think, is very much in tune with on my lecture videos, so making decisions on their product based on my criticisms, on cutting criticisms. Somewhere upwards of 10 views per video, right? So in general, my greenhouse geyser correction is going to be probably your best bet for this. And honestly, if we're at the point where the difference between your decision is the greenhouse geyser correction and your Bloom-Belt correction, what am I probably thinking about that? Probably pretty trivial, right? There's no right. It's also probably still. If I'm meeting for Bloom-Belt and missing on greenhouse geyser, probably not that big of a difference. There shouldn't be, people shouldn't be making large categorical decisions on strength of evidence there. So, but these are corrections that you'll see in your output, so just want you to know what those things are. All right, questions? Yes. Yeah.
Did you have epsilon hat finding again?
Yeah, this is just, so epsilon is your population metric. This is the greenhouse geyser estimate of that. Okay. Yeah. All right. So conceptually, kind of adding all this together, if I'm only observing participants one time, all the variability that I get due to just different people or different folks, right? All of that gets delegated into error term. Okay. So Brittany, if you're doing jury selection studies or something like that, right? All the differences that you get for different people doing different jury work, we don't know why they're different. They're just kind of in there, and it turns into kind of a big mess, right? Because who knows why they're differences? What are their biases, so on and so forth, right? But if I go through and I were to have those same jurors be involved in multiple different juries, and I could observe there, let's say we're looking at guilt bias or something like that. What I would probably find is that folks in the first jury who tended to lean more towards assuming the person who's guilty would probably have the same tendency as in the second one and the third one and the fourth one. So what I can do is I can start to look at that and pull that variability that's different than the person who's super liberal, thinks no one's guilty, and sort of doesn't think anybody's guilty, right? We can go through, if we're measuring people across repeated assessments, we can go through and pull that out, right? And so what ends up happening, the more individual differences that we see, the greater the extent to which people are different, what we tend to see is a higher correlation across our intervals, right? And the higher the correlation between those repeated assessments, the greater the power of our repeated measures design. So has anybody here done like psychophys search in the past ever? Yeah, something like that. Okay. So this is the thing. So for my dissertation, I had people hooked up with this basic like peripheral stress of skin conductance and things along those, right? Emily, what would you guess the correlation if I sort of hook someone up skin conductance and measure them in response to this film and another film and another film and another film? What would you expect the correlation of skin conductance to be across within an individual across the repeated assessments?
I mean, if it's like one after the other, it'll probably increase over time.
Yeah.
You're stuck to this thing, that's why.
Yeah. It's gonna be super high, upwards of like 0.9, things like that, right? And so we're getting a little bit of difference. I'm reacting more to scary films than sad film or than sort of neutral films and so on and so forth. But like my body's a kind of a system, it can't go jumping all over the place, right? So where I start now, if I look at my skin conductance across Bosch's skin conductance across Elizabeth's skin conductance, we're all probably gonna come in maybe at different levels and have slightly different level. And so if we're just looking at twin group stuff, we're all over the board. But if we're looking within persons, everything is gonna be pretty systematic, right? So we've got big individual differences, but very systematic within strongly correlated repeated assessments. And for those types of things, these are incredibly powerful designs, right? Now, if we get to a spot where we're seeing that my measurement at time 1 is unrelated to my measurement at time 2 is unrelated to my measurement at time 3, then I essentially lose all the power of my measurement designs. But I can't think of a situation where that would happen, right? Unless you have someone just trying to throw off your your study, but you would have to have the entire samples responding randomly to repeat assessments, which is an unlikely scenario. Okay, so with these designs, again, the power of these comes from the correlation across your repeated assessments. Okay? And as you start to get stronger and stronger correlations across your repeated assessments, that means if I know your size score at time 1, I got a pretty good idea what a score it will be at time 2 and time 3. And because of that, if we start to see differences across those things, even very small ones, we can start to tease out some pretty subtle effects. All right. Questions about our repeated measures designs here? What's going on within these models? Okay, cool. So what we're going to do is we're going to work through a couple of different examples here. And with these repeated measures designs, the thing that starts to become relevant, and we'll get into this, is how you're conceptualizing the nature of your repeated assessments. Sometimes with these designs, we're probably assuming some sort of systematic increase or decrease in increase in scores as we sort of go across time, right? That's going to be probably the bulk of the types of designs that you run. But sometimes what we're going to do is we're going to have people exposed to repeated measures, and we're not necessarily, the order is arbitrary, right? Like I have different versions of, let's say again, a jury vignette or something like that. And the order or sort of the changes across how people respond to those, I'm going to expect depends on what order I put them in. If the order is kind of arbitrary, it doesn't matter. This is a situation where we would have unordered means where we're getting repeated measures across multiple assessments, but the assumption is that if I just reordered things around, then I'd get a different pattern, right? Versus things that are more focused on time. I can't put your baseline in the middle of your treatment session and your sort of final session, sort of the second one, and things along those, right? So if I have some sort of ordered, sort of natural order, we kind of approach this a little bit different than if we have something that could sort of jump around. So we got two data sets. So make sure, so those are on the second years. Did I send you data sets? You have the data sets, or third years, second years, your second years.
You mean like SPSS files?
Your SPSS files.
Files are just screenshots of it.
Okay.
Like PDF thing, which is fine. I don't think we didn't get like actual files.
Okay, that's let me do that just so people Actually, can someone, so does someone have those files up or saved or something like that? Because,
If I have them and I can send them, but currently no license for SPSS exists on this computer.
Oh my god.
okay. Okay, Matt,
Work on sending them.
will you send those to other, does someone have SPSS open where it is working in here?
I'm trying that.
DJ, can I ask you to put in another call to IT and ask them what the hell?
Yeah. So SPSS.
License.
Yeah, the licenses installed.
If
We don't have to install.
Yeah, I think it's all the computers.
What's that? It's, what is it? Is it 766 help?
I think so.
Yeah.
I can look really fast. WWRT. It's 307. Yeah.
Okay. All right. Well, we're not gonna wait for IT to fix this. I'll go through, we've got, you all are capable of identifying pull down menus, knowing where that is. We'll start going through and working through screening stuff here. And hopefully we can get someone on board and get this all fixed up. Okay. So what we're gonna first do is we're gonna work first with these order mains, right? And so here what we've got is, we've got scores from folks on an inpatient psychiatric unit. We're assuming that they've gotten some sort of treatment for depression. And what we've got is we've got scores at intake, 2 weeks, 3 weeks, and 4 weeks. Or intake, 2 weeks, 4 weeks, and 6 weeks. So we've got 4 assessment points measured every 2 weeks. And what we're interested in is, are we seeing changes in the pattern of scores over time? Now, based on sort of just the conceptualization, what are we hoping to see in these data? Allie, what do you think? What's that? Yeah, we're hoping to see some sort of reduction, right? We're hoping that over time, we're seeing some sort of reduction, right? So this is a nice example of an ordered data set where we're thinking as we progress over time, we should see some hopefully systematic change in these data, okay? So what we're gonna do first though, is we're gonna go in and we're gonna start with a basic screening, okay? And again, I gave you all have in our handouts, your screening stuff. This is all gonna look super familiar because it's not terribly different than what we would do for the ANOVA stuff that we've done up to this point, okay? So first thing we're gonna do for this analysis, we're just looking at changes in these depression scores over time. So if I go through and I just sort, looks like I don't have any missing values here, right? So I know that there's nothing in at least the variables that are going to be going into this analysis. No missing values, so I'm looking pretty good here, okay? Then what I'm going to do is I'm going to go to Analyze, I'm going to go to Descriptives, choose that. Then I'm going to go down through and look at my BDI scores at intake, 2 weeks, 4 weeks, and 6 weeks. We go to options, ask for skew and kurtosis, continue, save my Z scores, okay? Josiah, why am I saving Z scores? So I can have my standardized variables so I can look and see if I've got anything that's sort of hanging out there and causing potential problems. Okay, I'm going to go through, I'm going to paste this and then run this in my data here. Okay. Oh boy. Okay, that didn't do anything. I was trying to make that bigger, But here, what we've got, and it will probably be difficult for trying to see if there's a way to. Well, I might be able to, but that'll take some time. Anyway, I'll just go through it. What's that?
There's a, what's it called, like the,
Magnifying glass.
yeah, magnifying glass, I forgot what that thing is called, buy the printing option, try that.
Yeah, I
Way
think.
to the far right.
Oh, whoops.
Oh, wait. And you can click. Save.
Where at now?
All the way on the end. Got
This-
it, yeah.
That, oh, that's just a search, yeah. So anyway, what we've got, I'll let you know, is we got 388 participants in our sample. Is that a reasonably large sample? Yeah, that's pretty massive, right? So we're pretty good here in terms of we're almost certainly going to not have meet our criteria for the assumptions of normality in the sampling distribution, right? So we've got a massive set here. Our minimum and maximum, looking at here, this is all going to be reasonable for our BDI measure. So we're not concerned that 0 to 63. We're all within bounds, so we don't have to worry about anything that's sort of weirdly scored or not a real score. I'm looking at my skew and my kurtosis levels. Here, we're starting to get some interesting stuff. And again, remember, this isn't just like checking boxes to see, like, have I violated assumptions? I'm also wanting to try and understand something about my data. At intake, I've got a skew that's functionally 0, a kurtosis that's negative 0.64. What does negative kurtosis look like? What does that describe? What do you think, Amanda?
That,
Yeah, that's the like kind of box. This is sort of kind of like to the square distribution, right? Not that I walk around like that, but that's kind of so what it is, right? So our positive kurtosis, right? That's the skinny point with the flat tails going out. So it looks like we've got no real skew, but kind of like maybe a kind of more of a negative kurtosis distribution. As we increase across my repeated assessments at 2 weeks, 4 weeks, and 6 weeks. By the time we get to 6 weeks, we've got a skew of 1.5, right? So we're getting increasingly positive skew, and our kurtosis goes from being negative 0.64 to positive 2. Okay. So based on those skew and kurtosis values, do we have any functional concerns about sort of our distribution based on our absolute estimates of skew and kurtosis? Probably not, right? By the time we get to 6 weeks, we're getting some positive skew and something that looks like some different kurtosis. But what's our real silver bullet here? So why we don't have to spend too much time worrying about this? Emily? Yeah, our sample's tremendously huge for this type of analysis, right? So we're feeling okay with that. So no real concerns here, but what we do want to do is we want to go through and I want to take a look at what these distributions look like with my own eyes, just because they're not something that could potentially be problematic for my analyses. Doesn't mean that there's not something that I might want to be aware of, right? So I'm going to go down to descriptives and I'm going to go to explore. And I'm going to look at my 4 BDI assessments here. Don't have any between subjects factors, so I'm not worried about that. I'm going to drop down my research ID in my identify label or my label cases by, so that I know if I got weird stuff, my box plots, what's going on. If I go to my plots, I'm going to request histogram. I'm not going to worry about stem leaf so much. So I'm going to hit continue there. And that's all I need. Okay. And go through and paste that. I'll run this and run my screen. So we're going to get all our descriptives. That's good stuff, but not anything we're going to worry about right now. So here's my histogram box plot for my BDI assessment at my first baseline evaluation. Natalie, what am I seeing here in terms of this, the histogram and the box plot here? What's that? Yeah, it's roughly normal. I got a lot of folks in this sample, right? And so I've got kind of this normal-ish types of thing kind of going on. Any concerns with my box plot here? No, okay. People want to overuse unremarkable, right? But that would be an unremarkable box plot. Okay, so fine, if there's nothing much going on, say it's symmetrical, otherwise unremarkable. There's nothing really to talk about here. If we go, what do we got going on? Now we're at 2 weeks. Someone help me out. What's going on with this distribution of scores here? What do you think, Basha?
Positive skew.
Yeah, we're getting some positive skew, right? We're seeing that in the distribution of my scores here. We're starting to get a positive tail. If I look down at my box plot, I'm seeing things are kind of compressed down here. I've got what's looking like more of a skew reflecting up here. And now all of a sudden I've got a bunch of little tiny dots here. Remember, these are labeled with my ID variable. What are these tiny dots telling them? Extreme values based on, defined as how in my box plot. Anybody remember? Evan?
I think it was the circles above 1.5.
3. 1.5 above what? Yeah, the interquartile range. Remember, with our box plots, we're talking about median-based statistics. My interquartile range is the distance between my first and my third quartile here. And so if I've got a value that extends beyond 1.5 times my interquartile range, that's going to show up as a little dot. Now, be careful when you're looking at this. If we start getting a bunch of them, they can start to be superimposed on one another. You can kind of miss things. So be sure you're being careful. Don't just, this is generally okay, but also always double check the number of scores that you have up here. But we're starting to see some more of a positive skew here. Not something that's necessarily concerning for our analyses, but something that's worth paying attention to, okay? What's going on at 4 weeks, Matt?
More positive skew.
Even more, right?
Yeah.
And if we go down and we look at 6, what do we get? Even more, right? And so what's going on is we're starting to get increasing skewness in our data. So from the point where we started out, where our box plot, we were comfortable describing it as unremarkable, by the time we get to 6 weeks, what are we seeing? Something that is quite remarkable for a lot of reasons, right? Okay. What's happening with our data here? Yeah, Emily?
Most of the people seem to respond to their BDI scores are going down, but some people are, or just like for whatever reason, their BDI scores aren't changing necessarily.
Perfect. Right? And this is the thing that we need to be thinking about when we're running our data. Like, we're not just doing screening for our health, and it's the fun thing we want to set at night, right? What we're trying to do is, one, check for violations of assumptions that's going to be problematic for inference analysis. Stuff like that. Two, we ought to be looking just to say, hey, what's going on in my data? Does this make sense? Now, just because something's doing something that makes sense doesn't mean it can't be problematic, but at least we know why it's doing it and we understand, right? Here, what we're saying is treatment looks to be effective for most people, but for some people it's not. And we're continuing to see people high up there. So that's kind of what we would expect, right? Here, the good thing is we've got enough people in our sample. Does it matter if this person is hanging out way up there in terms of stuff by the time we get to the end of treatment? Probably not. Like, this is going to be an extreme value, right? But with 388 folks, it's not going to be dragging. This person is not going to be independently dragging me so far out that it starts to throw off our estimates and stuff like that. So we do have differences in the distributions across our repeated assessments, and that's something to take note of. But thankfully, we have a large enough sample for this, so we don't have to worry about that too much, or trying to do weird transformations or things along those lines. I mean, we could run some transformations here, but now you're transforming something pretty normal and that kind of have those consequences. Here, we're doing all right with stuff. Okay. Questions about any of this? Okay. Checking here, folks, is all this kind of sort of coming back, ringing bells? Any questions in terms of sort of our decision making as we've gone up to this point? Okay. And then obviously here, in terms of your interpretation, if you're getting something like this, I don't expect you to list out every single sort of participant number who has something above the 1.5 times in your quartile range, right? You could just say X number of participants sort of above and things like that. So, I mean, if you've only got 1 or 2, it's nice to know who those people are. If it's at half the sample, you can start to condense that a little bit, okay? All right, so last thing we're gonna do is we wanna go through, what is the last thing we wanna do?
Z-scores.
Yeah, I want to take a look at those Z-scores just to see what else is happening here. Okay, so I'm going to go through, I'm going to cut my original descriptive statement. I know that SPSS saves Z-scores is just put Z in front of the label, get rid of save because I don't need to save Z-scores on Z-scores. I also don't need skew and kurtosis because that's going to be the same as my just regular distribution, and then just run descriptives on my Z-scores. Here, we're starting to get some stuff, right? At baseline, everything's lower bound is about 2, upper bound is about 2.6. That's fine, we're not too worried about that. As we get to 3, lower bound is 1.4, negative 1.4, upper bound is 3. 4 weeks, negative 1.1 to 3.3. So now we're starting to get some higher scores there. By the time we get to 6 weeks, we got a lower bound of about negative 0.9, all the way up. Now we're at 4.5. So we're getting scores that are 4.5 standard deviations above the mean of the sample, right? So these are cases that are going to be important to note, right? And so if we go back to our data set here, and I sort ascending, I can go down through and find back, okay, here are a set of scores that are sort of, I mean, 3.3 is kind of your rough, that's a Z-score 3.3 is going to be associated with a p-value of about 0.001, right? So if you want to say extreme scores or sort of something along those lines, I take a look at that. So, all right, we've got 3 scores here that are demonstrating very, very high BDI scores at the final assessment point. Sort of our assumption here is that these are going to be folks who are just not responsive to treatment. That's going to happen, right? Would we want to throw those folks out? No, that's going to bias my sample and stuff like that, right? Do I want to get nuts and go start transforming things around? Probably not, because PDI scores mean stuff to clinicians, right? It's a metric that people understand. And if I start taking weird inverse log transforms and things along those lines, it's going to be kind of, it's going to lose meaning, right? So here, wanting to go through and say, yeah, I do have some violation or some I have distributions in my observed values that deviate from normality, okay, very clearly, but especially by the time we get to the end, right? But is that necessarily a violation of my underlying assumptions of my test? Well, because the assumption is the sampling distribution of means, right? And even this last distribution here, right? If I were to take this, I were to take the mean of this and then sample with replacement from the same population, 388 scores from all possible samples of 388 that I could pull from this population, and were to plot those out and take the mean of those, what would the distribution of means look like? Yeah, it would be beautiful and normal, right? Pretty much the means are going to be about the same. Sometimes you're going to get some means that go this way, sometimes you can get them to come this way. But if I plot the mean of samples of 388 across all possible samples with replacement that could be drawn from the population, the mean of those distributions is going to be normal, and that's what I'm worried about in terms of my evaluations. I've got some extreme values, but not so worried about the extreme values because I've got a large sample that's going to be okay. So overall, I'm doing all right. Now you'll see here in terms of homogeneity of variance across repeated assessments, I reported an F max of 1.76. Again, that's not terrible. That says the ratio of the largest variance, which is going to be here, to the smallest variance is less than a factor of 1. So, or less than a factor of 2. So there's no real concern about massive deviations in terms of my homogeneity of variance across assessment points. Sphericity, we're assuming that sphericity is always going to be violated, so I'm not worried about that. And so that just kind of wraps up sort of what I've got going on here. Okay, so use this again as your template. Don't get creative for CJ and I's health. Let's stick with this. But people feeling comfortable about sort of basic screenings with the one-way model. We get more complicated when we get into 2. So now we get into mixed factorial. Now we're going to have between subjects factors and also within subjects factors. And so we just kind of exploded factorially in terms of things we can take care of, but we'll get to that when we get to that. All right, cool. All right, let's go through, take a break. Let's come back at 3:45. Quarter till when we get started up again. You should screen that. I thought this was a tier 1 university. I thought it was a tier 1 research university. SPSS.
I thought we knew where SPSS agreements.
Ah, unbelievable.
Yeah.
All right. Now,
Yeah, so hopefully it said they'd either call back or somebody was just gonna stop by, so either, hopefully those things happen soon.
I'm gonna throw them out. I'm gonna grab by the seat paint spots. And I'm like, get out of here. Unless you can fix this.
Talk to me when you get to.
Right. But we got that on camera. It's just Napoleon Dynamite chugged that water. All right. Any questions, big picture or small picture, about our repeated measures ANOVA, what we're trying to do with these simple repeated measures ANOVA models, or is there anything we covered up to this point? Like you have an understanding kind of when we might use these models and kind of what we're trying to do with these. Cool. Okay. So I think we should be back up and running. So, all right. Let me know, yeah, if we lost some audio from the other one. We've got, I think, a nice screencast, not from the second year cohort, but from the third year cohort on sort of all of this. So you can go back through, and if you're missing pieces and parts, you can pick that up as well. So, okay. So what we're going to do here is we're going to jump into the actual analysis. So if you want to pull up your PDF, the one-way repeated measures ANOVA for the ordered means. That will give you all the stuff that we'll be doing here. And so what we're going to do, we've gone through, determined that we're pretty good in terms of our assumptions. So I'm going to go through, I'm going to select analyze, general linear model, go down to repeated measures. Okay. First thing we want to do here is we want to name our factor. What's our repeated measures factor called? What do we want to call this for these data? How's time sound? People like that? We'll call that time. Okay. And number of levels, how many levels do we have for time in these data? 4, right? So we're going to say 4, and we're going to hit add, and that's going to structure our repeated measures for this. Then I'm going to go down, I'm going to hit define, and what I'm going to do is I'm just going to take my BDI scores and plug them in order into my within subjects variables there. Okay, and so this is our one-way ANOVA model, or our one-way repeated measures ANOVA. This is all. We don't have any between subject factors. All we're looking at is whether or not do we have evidence of changes in the pattern of means across our repeated assessments. Okay, so if we go up to some options here, I'm going to go through and hit contrast. So what we'll get is a time contrast, a polynomial here. You don't have to worry about that. We probably won't use it too much, but just note that that's where you get there. If I go to plots, there's different ways we can do this. I'm going to take my time and I'm going to put that on the horizontal axis. So my repeated assessment is going to be on the horizontal axis, and then I'm going to go down. I'm going to click include error bars. Oops, add. And I'm going to go down. I'm going to hit include error bars. So that this is going to go through and give me 95% confidence bounds, so I can kind of see that. And I'm going to hit continue. And then I'm going to ignore post hocs for right now. Marginal means, I'm going to ignore that for right now. Not going to save anything. You're going to go down to options. You're going to collect, request descriptive statistics, estimates of effect size, and homogeneity variance test. This is going to give us an error, but we'll just click it because it seems like it should be something that we might want. There's other things in there, but it's a little bit more in depth than we'll need to get into for this. So I'm just going to hit continue. And then I'm going to hit paste. Okay. So this sets up my model for my analyses. I'm going to go through and actually, whoops, before I do that, I'm going to do something else. I'm going to get analyze. I'm going to go down to correlate. Okay. I'm going to go to bivariate. And I'm going to go through and I'm going to take a look at correlation between across my 4 repeated assessments here. Okay. I'm going to paste that. Okay. So before we actually get into our analyses, going to run this correlation table real quick. Okay. And if we run this, you'll see this right here at the bottom of your sheet. Why, based on the stuff that we've talked about at this point, what might be interesting about this correlation matrix? Thoughts? What do you think, Basha? Yeah, say a little bit. So correlations seem to go down each 2-week time period. Can you say a little bit more about that? What's in what way?
Well, I just noticed at first in the
Uh-huh. Yeah. And so what is this evidence of? Yeah. And in terms of our assumptions, what is this kind of demonstrating for us? What was our new assumption that we kind of added? That's not a new assumption, but it's one we're now concerned with. Anybody remember the word? Yeah. sphericity, right? So we're saying that BDI intake in 2 weeks is correlated 0.6, but BDI intake in 6 weeks is 0.38, right? Same thing, BDI at 4 weeks and 6 weeks is 0.75, but 4 weeks but 4 weeks and or 4 weeks and intake is 0.44, right? We're seeing different levels of association across sort of where we're going through, all suggesting that we probably have a very clear violation of sphericity, where the variance in sort of terms of the distance between these things is probably not the same as we're going across, right? So this is just a nice way of demonstrating that, yes, as we go through and run these types of designs, we see the types of things we were concerned about in terms of the violations of that sphericity assumption, right? We're always going to assume we've just violated it, but it's also always kind of interesting to go through and take a look at your correlations to see how things are related to one another, just to kind of know what your data is doing, okay? So that's good. We checked and found evidence of something we already strongly suspected was going to happen, but it's nice to see it in person. So going to go through and run our model. Okay, we first start out with a warning, right? It says homogeneity specification will be ignored because there's no between subjects factors. Homogeneity of variance will only test homogeneity of variance in SPSS. It'll only test it between subjects, not within subjects. So that's just what that's going on. But anytime you get something that says warning in a statistical output, you should always sort of attend to that and make sure that you understand what's happening here. So, but if we go down and we take a look at our within subjects factors, we see that we've got for our time variable, we got BDI 1, 2, 3, and 4 all lined up. So we don't have that all jumbled around. That's an important thing to take a look at. Here we're getting our means and standard deviations across our 4 assessment points. This is where we're going to test our F max. Okay. So again, our F max was just the ratio of the largest variance to the smallest variance. So do we have variance in this table? Nope, we don't. We have standard deviations, right? Just out of curiosity, someone with the calculator, what's 12.688 divided by 9.551? 1.328. Okay. Is this what we want? Is this our F max? Nope, it's sure not, right? What happens if we take 12.688 squared? What's that number? No, 12.688 squared. So the variance of what's that? 985 over what's 9.551 squared? Okay, and if we divide those, what do we get? Seven, we'll call it 7.7. Okay. Those two numbers aren't the same, right? So again, remembering it's the same thing when we're talking about standardizing our effect sizes and using the square root of the average variance as opposed to the average standard deviations. They're different, right? So you want to make sure that you're doing this correctly. So that's no good. We don't care about that. But here, the ratio of the smallest variance to the largest variance is only a factor of sort of 1.8, right? So this is well within bounds. So we're not concerned about this. Now, if we're 3 or 4 times sort of different, then we're going to start to get worried about stuff. The nice thing here is we're always going to have on our repeated measures, we're always going to have the same number of people at each time point. So we're not having to contend with unequal variance and unequal sample size, but always something we want to check out here. Okay. So we're looking good. And this is just your F max, remember. So we're looking good there. Now, when we go down through, and I guess sort of looking real quick at those descriptives, Erica, what are we seeing in terms of our mean values as as time goes on? Yeah, we're getting a decrease, right? So already we're not quite there yet, but we're seeing at least visually absolute values are starting to come down in the way that we would expect, sort of based on the design, right? So that's something important to note that we're kind of happy about. Now, if we move down through, we'll see multivariate tests. Okay, this is an alternative test for repeated measures designs that runs your repeated measures analyses more like a MANOVA style analyses, which at one point people tended to do because your MANOVA doesn't have sort of the same sphericity assumptions and things along those lines. But we're just going to ignore this because sort of it's not sort of more consistent with convention. Okay. Here's Matchley's test of sphericity, right? We're very clearly saying that we have violations of sphericity here, but again, we're going to ignore this because it's sensitive to deviations from normality, and we know that by the time we hit, we got a pretty good skew going on this stuff. So again, we're always going to assume that we've violated this sphericity assumption. So the fact that it's telling us that we have violated is not terribly informative. Here, Sam, are those epsilon estimates. If you actually want, at the end of the Matchley's test, if you really wanted to know what epsilon was and sort of what if that was relevant to sort of doing something, say you were looking at some more nuanced thing and you needed estimates, that's sort of where they're at, right? So these are the estimates of epsilon that are being based on, this is what's being based on down here, but we don't have to worry about this too much. What we are going to look at is our test of within subjects effects. And if we look at this, we see that we've got a number of different lines. We've got our sphericity assumed, right? If we assume sphericity, we have a set of tests. We have our greenhouse geyser, our Hohenfeld, and then a sort of a lower bound test here. Now, does anybody notice anything interesting about corrections for all of these tests? What's happening? Yeah, Emily? Yeah, all the F values are the same. Okay. So we're not seeing an effect. If we're just running a straight one-way repeated measures ANOVA, we're not seeing a sort of a sort of something sort of going on here. When we start running into a mixed factors ANOVA, when we start working on sort of condition stuff, between stuff, we'll start to see the impact of some of those corrections. Okay. So if we look at this, it really doesn't matter which one we choose because they're all giving us the exact same F value. Someone give me an interpretation. What are we seeing here? What is this test telling us? Yeah. Yeah.
Oh wait, the within or the between?
What do we have between subject factor?
Oh, no.
No.
Sorry, I saw the word between.
Yeah.
So basically it's saying that, like depression, the VDI scores over from 0.1 to 0.4.
Okay. On the right track, does this test tell us that they've decreased?
Or they changed, there was a difference.
Yeah, they're different, right? And so this starts to get into this is a technical aspect, but an important thing to think about. This is not looking technically at like systematic change. That's going to be looking at like an HLM or a growth function or something along those lines, right? All our repeated measures ANOVA is saying is that the pattern of means are different. It's testing, and remember our null hypothesis here is that the mean at time 1 is equal to the mean at time 2 is equal to the mean at time 3 is equal to the mean at time 4. If I find evidence against my null hypothesis, it just means that these means are different somewhere in there, right? And that's all that means, okay? But looking at those descriptives when we started gives us a pretty good idea of probably what's going on with this thing, okay? So if we go through and we take a look here, we can say, yeah, and with an F of 427, like that's That's a very, very small p-value. Okay, quick note. We didn't police this too much in the first semester, but when you're reporting p-values, like 3 digits until it gets to be something like this, less than 0.001. And then just for this class, go through and report that in sort of exponential notation, right? So it's like double click on this and it'll pop up and it'll say like 2.67 e to the negative 14 or something like that. Put that in there, okay? Don't sort of pull decimals way out to that. Same thing with like t statistics and f values is 2 decimals is fine with that, okay? Correlations, you can go 2 to 3. If you're calculating, you're running calculations with correlations, take your calculations out to 3 decimals, but as you're reporting it, 2 or 3 is fine. Just what it starts to get hard to track if you're seeing sort of correlations pulled out to like 15 decimals and things like that. But here we've got very strong evidence, right? Basically, with this F value, this is saying that if in the actual population of inpatient individuals receiving this intervention, if there was no change in depression scores in the population, these data functionally couldn't exist. Like this is a ridiculous F value, right? So really, really strong evidence that we have something going on, but we don't quite know what yet. We suspect, but so this doesn't actually tell us what's going on with the data. Okay, questions about this? All right. Beneath this, we have test of within subjects contrasts. We won't worry about that right now. We'll get into that in just a minute. That's testing some different trends going on in the pattern of means. Our test of between subjects effects. Now, we don't have any between subjects factors here, but we do get an F test for the intercept that's even bigger than what we got an F test of like 1,158, right? Any guesses of what is this between subjects test telling us?
Are they changing?
Okay, that's a repeated measure. That's if people are changing over time. Remember, so we start out with this.
I don't like the test as a whole.
What test as a whole?
Time.
Still kind of stuck on the within. Remember, so our effect that we're talking about, differences across repeated assessments. If we take our variance, and so this is the total variance, where's our evidence for our differences across time, systematic differences across time? Where does that exist in this decision tree? Yeah, that's over here. Our test of between is just a test of whether or not people are different in their means, right, across people, right? And we have very, very clear evidence that people are different than other people. So in the absence of some grouping factor where we would have sort of maybe sort of different treatment conditions or something like that, all that is telling us is that, yeah, what we have is that the variance that we're pulling out due to individual differences is not equal to 0. And it's very, very, very much not 0, which is what we would generally expect, but good to know where these components come from. And again, so thinking about if we're looking up, and this will start to become important for the calculation of effect sizes, we're within subjects of okay. Different components to our sums of squares in this one-way analyses, right? So where is our sum of squares between? Anybody, any guesses in where we would find that in this output or what that number is going to be? Who's that? Yep, exactly. It's going to be 131,571.531. That's just all the variability of the total. That's the stuff that's due to just individual differences. Okay. What about my sum of squares for my effect? Can someone tell me what that number is going to be? Guesses?
Said what, your sum of squares for your effect?
Yeah, for my effect. Where does my sum of squares effect live in this output here? Yeah, is that?
I'll just guess again. It depends within subject, effect.
Yep.
and then all those top four ones are the same.
Yep, that's 69, 586. Perfect. And Josiah, take us home. Where's the error? The one beneath that, right? So you can see within the output. And so this starts to become really, really important in terms of as you start to move forward, doing more advanced types of analyses and doing this type of stuff, being able to go through your output and be able to know where and interpret where things are going. This is pretty straightforward. We've got our between, we've got our effect, we've got our error. Sort of being able to pull those through and sort of drop those where they need to be going with things. Okay, this is all variability in my outcome. This is a variability in my total set of depression scores that's just due to individual differences across people. This is the variability that's due to sort of changes over time. This is variability due to just sort of differences within people that aren't captured by that. Okay, so just keeping track of where things are put together and plugged in with stuff. Okay, we've got our within subjects. We don't worry about that for right now. Our between, and then here's our plot of scores over time. New version of SPSS allows us to put in confidence bounds, but thinking ahead for how we're going to go through and test whether or not we have evidence of reductions. And so like where this is all coming from. Robert, if I'm looking this, am I going to guess that I'm probably seeing differences across these individual assessment points? Yeah, I can eyeball that with those interval estimates, particularly with the repeated measures, and there's no overlap at 95% confidence intervals at each one of those. I mean, we'll go through and run some tests, but that graph, I don't need to. I mean, I already know that this is different than that, that's different than that, that's different than that. These two are different from one another, right? If we want to put a p-value on it, cool, but just this alone, graphically, with the confidence bounds, I already know what the story is going to be here. So just going through and taking some note of that. Right. Questions on this analysis, kind of what we did here. Okay, cool. So let's go through and do this just one more time, except this time let's pop open the other data set. Okay, this is going to be a little bit different or a lot different. What we've got here is we've got a data set where what we want to know is whether or not people are okay staying friends with hypothetical survivors of different types of life stress, right? So we know that we've got all sorts of different types of traumatic events, but not all traumatic events are created equal. What we want to know, we're interested in sort of people's support or willingness to provide support for survivors. And so what we've done is we've gone through and we've created a number of different scenarios. So we've got 4 of these that correspond to sort of what we typically think about as sort of typical trauma or conventional trauma. So we've got a motor vehicle accident, combat deployment, sexual assault, and natural disaster. And then we have scenarios that have other types of very, very stressful things, but things that we wouldn't probably qualify as trauma. So we've got infidelity, chronic illness, work relocation, lost all my money. Okay. And so what we've done is we've gone through and we had people go through and we gave them these different scenarios and had them rate how much they'd be willing to be friends with or maintain friendship with hypothetical survivors of some of these outcomes, right? Now, do we have an ordered situation in terms of these analyses in the same way that we had with the BDI. No, we don't, right? These are all arbitrary. I mean, I have to give them in some order, but the order is sort of makes no difference. No, well, it could make a difference, right? And I want to think about that, right? If I respond first to sexual assault and then to work relocation, right? I'm going to get a bit of a contrast effect with this, right? But there's nothing inherently sort of ordered about the how I present these out. And so it's going to change the way how we think about this a little bit, okay? For this study, what we ended up doing is randomizing this. So people got things in random order to kind of sort of clear out sort of potential, what will almost certainly happen in terms of carryover effects. But if they're all randomized, then hopefully everything turns out okay, okay? So if we go through and we pop open this set, what I'm interested in, and we're not going to go through and screen all this because you already know how to do that. I'm just going to go through and I'm going to look at, see if I have any missing values. I do not. Okay. So we're going to skip over the whole piece of things where we're running the screening and assume this is fine, which is maybe not a good assumption, but we'll not worry about it right now. We're going to go to analyze. We're going to go to general linear model, repeated measure, and I'm going to name my repeated measure vignette. Here I have 8 different levels, okay? And so I'm going to define this. And what I'm going to do to just trying to create some sort of reasonable order with this for me is what I'm going to do is I'm just going to load in all my sort of criterion A, like my actual like clinical trauma stuff and the other stuff that's stressors and not trauma here. So we'll put car accident in there, combat, assault, and disaster. And then we'll drop in all my other non-trauma stuff. Okay. I'm going to go down through and plots, put that on my horizontal axis, add that, include my error bars. Options, effect sizes, descriptives. We won't click on homogeneity tests there because we already know that'll give us an error. Okay. And I'm going to hit OK. All right, so you have a handout worksheet for this. Also, if you look at the front page of this, you'll see I put together a correlation matrix for this. Looking at the correlation matrix on that handout, Basha, you had identified this before. Are we seeing the same systematic pattern of correlations across these associations? No, we're not, right? Because one of the things, I didn't give these all in order. Maybe if I had, we might see something, but these are all different vignettes, different short vignettes delivered in counterbalanced order. So we're not seeing sort of the same type of thing. So that's good, but does it look like we may have violated, still have a violation of sphericity?
Well, yes, I guess we do have a violation.
Yeah. So we're not looking at time, right? But remember, our sphericity assumption assumes that if I were to take people's scores from all possible combinations of these 8 scenarios, and if I were to take their score from one and subtract it for the other, that I would see equal variability across all of those different scores, right? Now I'm looking at this, I'm seeing that that's probably not going to happen because I have some things that are going to be more tightly correlated than others. So it looks like people's willingness to provide friendship after reading the car accident versus the disaster scenario, those two responses are correlated about 0.75. But if I look at sort of the correlation between whether or not people would be likely to provide friendship to someone who has been exposed to combat versus whether or not a friend who's relocated, That's a much different correlation, suggesting that there's probably more variability across those scores than the two other sets of scores between accidents or disasters and MVAs, suggesting that we're probably getting differences in terms of how closely these two things are related to one another, right? So we still probably have a violation. It's not as orderly and systematic as in the previous example, but again, this is why we're always going to assume that we just have some violation of sphericity and just move on to our corrected tests. Okay. Questions about that? All right. So going down through and taking a look at, we look at our descriptive statistics. Allie, what are you seeing in terms of descriptive statistics on this?
Like, more or less likely to, I guess. stick with those two.
Yeah.
Differences, but it's not. There's nothing huge.
Yeah. So if I'm looking at that, that's a lot of sevens, right? And it's a lot of sevens falling somewhere between 7.1 and 7.6. If I'm just looking at this, Rachel, are you excited about the possibility of us finding differences across these? Probably not, right? Things are looking pretty grim at this point, right? Particularly if we compare the difference across these to the standard deviation. I'm thinking that we might have just turned up a bunch of null results with this, right? So yeah, the absolute values are different, but it's not looking like we're getting huge discrepancies across this, right? So if we go down through, we progress, we got our multivariate test, we ignore that. We look at our tests of sphericity, we still see that we've obviously violated that, right? And we have these epsilon values that are actually even a little bit lower than what we had seen before. But again, we're not going to put too much into that. We're going to ignore that and progress just on to our test of within subjects effects. And Rachel, what do we find though when we get to our test of within subjects effects? Yeah, we got pretty strong evidence for differences across these means, right? This is saying that across these 8 different vignettes, we very clearly have differences in the pattern of means across these repeated assessments, okay? Now, this is a large sample, right? We've got how many people in here? 231. So we got a reasonably sized sample. But if I were to go through and compare any one of these in just like in a between groups type of a situation, I can tell you I'm not going to find differences here, okay? Everything is too close to one another. But if I go through and I set this up to be a repeated measures design where I've got the same people rating each one of these vignettes, and we go through and we pull out all of the individual differences, the reason because Rachel doesn't want to be anybody's friend, so she rates everybody low. Katie wants to be everybody's friend, rates everybody high, right? All those differences and everything in between, we start to be able to parcel that out because we're getting repeated assessments. We can pull those trends out, attribute those to individual differences. And so what we can do is we find very clear evidence of differences across these ratings, even though if I were to run this as a between subjects design, so let's say I've got 30 people responding to one vignette and another 30 reading another and another 30 reading another, this whole thing would have come out to be a wash. Okay, so really emphasizing the power of these designs for trying to tease out subtle differences in things. Okay, and so the same thing, we have our between subjects, tested between subjects effects, which says that people are different than people. But if we go down through and we take a look at our graph, like, I mean, this makes it look like there's a whole lot going on, but that's a function of scale, right? Our scale goes from 7 to 7.8. It's not even a full level, right? This is on like a 0 to 8 scale, right? So in general, people are saying, yeah, I'm willing to provide support to people. But
That's kind of a loaded question, right? Like you got to be a real jerk, be like, oh, hey, yeah, no, screw that person because they got in a car accident. I'm not here to help them out, right? So the whole thing is biased against actually finding effects here. But given the design and the size of the sample, we've gone through and been able to tease things apart, right? Now, do we see a clear orderly effect sort of in these data? Not really, right? It's not like the last one. We had a nice polynomial trajectory, something that looks like maybe a quadratic or a line, right? So we've got sort of more stuff going on with this, which means that we're going to have to think more carefully about how we want to go through and tease this stuff out. But based on our omnibus test, we have very, very clear evidence here that we do have support for differences in how people respond to these different vignettes, sort of based on trauma type. Okay. Questions about this? People comfortable with kind of how these analyses are going, kind of what we're doing with this? Okay, cool. So let's pop back into lecture land here. Thinking about formal write-up, right? Because there's not a whole lot to say. I mean, they're pretty straightforward. The null hypothesis is that all the means are equal. And so just based on our omnibus tests, there's not a whole lot we can say. But here again, we've got a couple of different examples of how we can go through and sort of maybe sort of summarize what we've found. So results of repeated measures ANOVA, decisive evidence against the null hypothesis of equal depression scores across repeated measures, or repeated assessments in the hypothetical population of individuals repeating in patient care. And this is hypothetical population because this is assuming that if we took all people who needed inpatient care and provided them with sort of this specific type of intervention, this is what we would get. Inspection of observed means indicates substantial reductions in depression over the course of intervention. I mean, this is just kind of eyeballing it, right? There's no real tests here. With our post-trauma support, we have evidence within subject effect of event identifies data from the current study is incompatible with the expectation of equal willingness to maintain friendship for individuals exposed to different forms of external stress. So I'm just kind of playing around with different ways of saying this to kind of give you different examples. Results suggest that specific events may influence others' willingness to provide and or maintain support following exposure to stressful experiences. We're not saying where that difference is in. We're just saying that, hey, based on what we've got evidence that there's something going on in there somewhere. So again, you all have calculated, but again, S value, remember that this is sort of evidence equal to someone telling you that they have a fair coin and flipping 471 heads in a row. It's pretty compelling evidence against a fair coin, right? Basically, these data can't exist with a fair coin functionally, right? Same thing, sort of the Bayes factor is, I don't even know what that number, I was going to say billions, but that's way bigger than billions. Same thing here, even with this, where we had a more subtle effect, we still get an S value of 65, right? So if Kansas City gets 65 heads in a row, I'm going to call up the NFL about their overtime rules because that seems like maybe not fair, right? So again, if we're thinking about interpretive standards here, for the Bayes factor, anything over 100 is decisive evidence, right? So we're very clearly above that. So just thinking about this stuff as we're putting this together. Okay. All right. So thinking about effect size, we saw effect sizes in there, but we didn't actually address this. That's because effect sizes get a little bit tricky when we're talking about some of these repeated measures designs. Remember that our eta squared indicates the proportion of total variance associated with an effect. Okay. And this is just your sum of squares of effect over your sum of squares total. This is essentially your equivalent to an R squared, right? It's just saying of the total variability in depression scores, X percentage is associated or attributable to changes over repeated assessment. Okay. Problem is that our eta squared sensitive to the number of effects in their design. Remember this, we talked about this when we went from our eta squared and our one-way ANOVA to our factorial ANOVA. Basically what happens is the sum of squares associated with your individual effect is going to start to overlap to some extent with other effects, even if you've got a completely randomized design, just because the correlations aren't going to be exactly zero between things. And so as my design gets larger and larger, the sum of squares uniquely attributable to a specific effect is going to start to get chipped away at by other things. And so my concern is that my eta squared, my one-way study is not going to be exactly comparable to my one-way or to my eta squared from my 2x2 design. And so we have some concerns about comparability across effect. And so what we are concerned about is, even though we know eta squared is an overestimate of the population effect, if I'm comparing eta squared to eta squared across different designs, it's going to potentially underestimate sort of comparatively across things. Okay. So we talked about partial eta squared as a alternative, and our partial eta squared, remember, provides an index of effect with respect to unexplained variability in my data. Okay, so here our partial eta squared is going to be sum of squared effect. So the numerator is the same, but the denominator is sum of squared effect plus my sum of squares error. So if I've got here's all my variability in y, right? Here's x1, and here's x2. Okay. Eta squared says of all of y, how much of this is attributable to uniquely attributable to x, right? And that's just going to be of the total that section right there. Okay. My partial eta squared is saying of the stuff that's not of the variability in my outcome that's not explained by other things, what's attributable to x. Okay. Now my denominator isn't all of y, it's this piece. Okay. Once we've accounted for and taken stuff out for attributable to the rest of the model, of whatever's left over, how much is attributable to my effect. Okay, so Josiah, in this situation, for eta squared or partial eta squared, which one of these is going to have the larger denominator?
Larger denominator?
Yeah.
Eta squared.
Eta squared, right? And if it's a larger denominator, that means it's going to be systematically smaller, right? So as I go through and have other factors in my design that start accounting for variability, it's going to chip away. So that denominator is going to be smaller. I'm not talking about the whole piece of the pie. I'm talking about what's left over after I account for other stuff. Okay, this is going to start to be really, really important in interpreting partial eta squared or partial correlations, semi-partial correlations, and things along those lines. So eta squared is nice because it has kind of good interpretive value, right? Like for all the variability in my outcome, what proportion is uniquely attributable to this, right? That's an easy thing to think about. Partial eta squared, less easy to think about. Like after I account for other things, like of what's left over, how much does this account for? But it's something that ends up being a more comparable estimate of effects across different types of designs. Okay. Now, the problem is that for our partial eta squared, people have made the argument that it's problematic for a repeated measure design because for a repeated measures design, we have multiple sources of error, right? In our between subjects, we just have one error, right? We just have effect and then error. In our repeated measures design, we have error due to between subject stuff, due to individual differences, and error due to sort of differences, unexplained stuff across the repeated measures, right? The problem is when we go through and we take a look at our eta squared, or excuse me, our partial eta squared in our output, that's just only considering the repeated measures error component of things, and it's leaving that between error out. Like when we went through and looked at those error terms for the between stuff, was that a small amount of error or a large amount of error? What do you think, Robert? It was massive. It was massive because the majority of the variability we're seeing in the data is due to just individual differences across people, right? The problem is when we calculate partial eta squared as indicated in your SPSS output, what it does is it takes all that and doesn't even include it in the thing. It's only looking at the within subjects variability. And so the argument and the concern is that if I look at my partial eta squared in a repeated measures ANOVA, it makes it look really big. And so then I go into like, oh, I got a large effect, and I try and run that in a between subjects design, and I've wildly overestimated what's going on. The repeated measures design goes through and takes all that between that individual difference variance out, which is generally the biggest source of your error, sets that aside. And so your denominator is much, much smaller even from the beginning, okay? And so the concern, again, is comparability of these effect sizes across different designs, okay? People see kind of what's going on with this, okay? So some solutions, and you'll be reading a paper on this, is a metric called generalized eta squared, okay? Generalized eta squared is a metric, and it basically just takes that between subject stuff that we sort of didn't include, and it just plugs it back in, okay? We can calculate this pretty easily from SPSS, but the specific formula, what goes into generalized eta squared, is going to be dependent on the design and sort of what types of effects that you're looking at, okay? And eta squared, or generalized eta squared, it's going to get even more into the weeds on like methods stuff that we in clinical stuff will generally ignore. Experimental folks tend to get more in sort of the traditional experimental design, sort of separating out and treating differently factors that are manipulated factors versus individual difference characteristics, things that are just existing right out in the universe. And so the complexity of generalized eta squared is that you have to understand sort of it's going to change depending on what type of design that you have and where your components are coming from. The nice thing is, or the proposed benefit is that if I go through and I calculate a generalized eta squared from a repeated measures design, it should be comparable to an effect size if I were to calculate generalized eta squared in a between subjects design. Those two things should give me sort of put everything on an equal metric so that I can make sort of reasonable comparisons or reasonable inferences about the size or the magnitude of my effect that I'm looking for, okay? So for our one-way repeated measures ANOVA, which this formula will change if you get into sort of different types of designs. For my one-way repeated measures ANOVA, my generalized eta squared is just going to be the sum of squares for my repeated measure over the sum of squares for my repeated measure, my sum of squares error, and my sum of squares between subjects error. It's going to add all those things together. So relative to my partial eta squared, which is going to be sum of squares RM over sum of squares RM plus error, or sum of squares error RM. Okay. What did we do with our generalized eta squared here? Took that big ass chunk of error variance that we had sort of taken out from our effect, and we're plugging it back into our estimate of effect size. Sam, what's that going to do to the estimate of my effect size? Yeah, it's going to drop it way down pretty dramatically. Okay. So pretty straightforward calculation for the one-way design, but as we start to get into more complex factorial designs, there'll be some other things you'll need to take into account. And so it's important when you're looking at your output, knowing what those different sum of squares components are, what they represent, so on and so forth. Okay. All right. Questions? All right. So yeah, Bakeman will argue, so it's the generalized zeta squared is nice because you can sort of comparatively comparable across a number of different designs. And so generally should be, so the argument is reporting generalized zeta squared over some alternatives. Bakeman 2005 has details for calculation. You'll be working through that paper and sort of drawing calculations there. From a practical standpoint, no one makes you report generalized zeta squared. It's like you taking the high road. The thing that you'll need to recognize is if you do report generalized zeta squared, it's going to be it will often be a very small effect, right? So you'll need to be able to be thinking about how to communicate that to people, making the argument for, yes, this is very small. What you can do is probably, and this is what I would do, is report partial zeta squared and generalized zeta squared together. So you say, hey, this is kind of what this is, but if we do this other thing, this is kind of where that's at in terms of thinking about absolute magnitude of effects, okay? And this makes some sense because our repeated measures designs are so powerful that sometimes when we get very, very clear evidence for an effect in our analyses, that's good, but that actual effect that we're teasing out within the context of all the variability in our data can actually be pretty subtle. It's just saying that sort of our design is very powerful. But if I wanted to compare what I'm seeing here and change up the design, that could massively change sort of my likelihood of detecting something. Okay. All right. So here on this slide, gone through and calculated generalized zeta squared for both of these examples. Okay. So generalized effect for the main, generalized zeta squared for the main effective session indicated the repeated assessment accounted for over a quarter of the within and between subject variability and BDI scores over the course of intervention, right? So this is me just pulling error terms or sum of squares terms from the output and calculating my generalized zeta squared. But if I go through and I take a look at eta squared or partial eta squared for this analysis, it was 0.525. So basically it's cut the effect size in half, okay? Same thing for my post-trauma support. Generalized zeta squared indicated that event type accounted for about 3.8 of the reduction across within and between subjects error for ratings of willingness. This is just me playing around with different ways you can go through and interpret this, right? My partial eta squared for this is 8.3%. So again, we more than cut that in half, right? So this is just recognizing that our partial eta squared is just looking at, it's only focusing on this piece of things and keeping all this stuff out. But the problem is we end up with an effect size metric that isn't directly comparable to analyses or studies that may have done a completely between subjects effect. Generalized zeta squared is saying, nope, can't cheat, got to throw that all back in if you want to have some comparable metric of effect. Okay. All right. Questions on generalized zeta squared, partial zeta squared, Venn diagram. We're going to be all about Venn diagrams this semester. Venn diagrams. Oh, I'm not. That was funny for a reason that was like apparent to me like 2 years ago, but I can't remember why now. Yeah, that's Lionel. He's much fluffier right now, but he will not be because he's getting a haircut on Tuesday, I think. So, what's that? Yeah, he does get groomed because otherwise he'll get matted up pretty good. Actually, he does better than our other cat, but they're all going to get shaved down soon. So, all right, I'm going to finish up with talking about. So we've got our omnibus effect. How do we go through and start teasing out specific effects, right? This is all going to be straight up, almost entirely 95% review of where we finished off last semester, okay? So again, our omnibus effect just tells us that there's something in there somewhere, okay? Problem is with our repeated measures design, we have additional assumptions and the possibilities when we get into mixed factor stuff of having both within and between subjects effects to calculate to account for. And so we need to think very, very carefully about how we're going to go through and start probing these omnibus tests. For specific effects, got some trend analyses. Basically, this is looking at, do I see a linear trend or a linear reduction or a linear increase over time? And what we can do is we have some tests we can go through and sort of test that specifically. We have linear contrast plan comparisons, just like we had before. We also have post hoc testing. The strategy we're going to use is going to be based on some specific hypotheses. Always with these designs, before you get started, have a very clear set of hypotheses about what you're expecting stuff to do, right? That doesn't mean you can't poke around and look at some exploratory stuff that's going to make your life a hell of a lot easier if before you start, you have some clear idea of what this data should do and what's going to be important to test, okay? You're going to have some conceptual considerations, study design, number and type of effects you're going to observe, right? So think about where we ended up last semester, where we had our factorial analyses, where you had like a 2x3 and all the possible comparisons. Now add multiple assessments for all of these. This can get out of hand real fast if you're not thoughtful in how you're planning to go through and probe things before you go through and run your analyses, okay? The quick review of our multiple comparisons. Remember that our per comparison error, this is our probability of committing a type 1 error on any given test, right? We set this as our alpha, and we're saying for any given test, this is the likelihood of us saying we have something there when we actually don't. Family-wise error. This is a little bit different. This is probability of committing at least one type 1 error across a series of comparisons. This is where we get into our Bonferroni inequality. We calculate this specifically as 1 minus 1 minus our alpha level taken to the power of the number of comparisons that we have, right? So if I run 4 comparisons all at alpha 0.05, my family-wise error rate, the probability of me committing at least one type error across those 4 is much higher than the original alpha level I put together, right? So we need to be thinking about this. Our family-wise error bounded by our alpha and C times our alpha, right? This is how we get our Bonferroni correction. So I'm running 4 comparisons times alpha 0.05. Your actual family-wise error will be somewhere in there, but it's going to be close to C times A. So recommendations, always be selective, be thinking about what's meaningful given your design. If you dive into testing all possible comparisons, you're wasting power because you're going to have to correct for all that stuff. And then what's going to happen is you're going to have a bunch of stuff that you're not interested in talking about, but you went through and ran the comparisons anyway, so now you're going to have to talk about them. Remember last semester, some of the stuff where you did post hoc stuff and you had like 50,000 things to talk about, and it was hard to figure out why that would be interesting or meaningful in the first place. That's just what happens if we're not careful and are just going through and running things, okay? SPSS also isn't going to do this for you. It's just going to run things, and it's either going to correct too much or not at all. So we need to be thinking about how to go through and plan before we jump in and do this stuff, okay? So rule of thumb, always have a good reason for looking at the tests that you're wanting to compare, okay? And doing this beforehand, thinking about this is how I expect things to work out, is going to be a better strategy than running stuff and then getting like that vignettes pattern that's kind of all over the place and like, oh, well, I want to see if this one is different than this one and this one is different than this one for no other reason than they look different, but I have no good conceptual reason for why those might be different. It gets me sort of tied into a bind that makes it difficult to go through and tell a comparing narrative, okay? Our a priori comparisons, these are going to be theoretically meaning comparisons that we determine before we go through and collect the data, or if we're looking at existing data before we actually run the analysis, right? Where we're setting these up as linear contrast, independent sample t-tests. If I'm running just a handful of these, just planned comparisons, I generally just, if I called my shot before I did anything, before I even collected the data, that gives me sort of conventionally, sort of gives me leeway to go through and run those at per comparison rates. I don't have to handicap myself because I called my shot. Now, you can't have 15 a priori comparisons that you want to run. That's cheating. But if you start to get some more, you can start to apply that bond parameter without static correction if you want to be conservative. But again, make the determination on whether or not you're going to use those corrections before you actually run the comparisons. Or not. Once you run it, it doesn't make sense to apply bond parameter correction. Then you make these determinations before you do it. Okay. Post hoc comparisons. This is looking at generally exploratory stuff. All pairwise comparisons. We typically sort of generate sort of our interests with this after we looked at all the observed means, right? And what happens as soon as we've looked at those observed means and then determine what we're interested in, what we do is technically we don't get taxed for it. Because in our head, in that split second, I just ran all possible comparisons because all possible means, cherry picked the ones I thought were the biggest. And so now I should probably get corrected for all of those, okay? We can get this easily in SPSS, right? And it goes through and corrects for family-wise error rates to some extent. The problem is if I'm only interested in a couple of things and I just got taxed for 15 things, I've just taken a big hit on my power unnecessarily because what I'm doing is getting charged for a bunch of stuff that I didn't care about talking about anyway, okay? So it's always exciting to go through, run our data, see what's happening, see what's turned up. But please go through and think carefully before you go through and run those analyses or look at stuff to say, what's interesting, what's most meaningful, why did I run this study, and what's my strategy for going through and testing things. So again, from a methodological standpoint, that limited planned a priori contrasts, more theoretically and methodologically defensible, okay? You'll get pushback from reviewers. Well, why didn't you look at this or why didn't you look at that? Like, well, because I wasn't interested in that. That's not why I did the study. Yes, you could. A person could look at those things. Here are means and standard deviations. If you want to do that, you have all the information you need to do it. But I don't want to talk about 15 things that aren't relevant to my main hypotheses. These are the reasons that I've laid this out. And sort of a lot of this is building this in the introduction of your theses, dissertations, publications to say, this is the study I'm running. These are the things I'm wanting to test. These are the hypotheses I've laid out. You're in much better position to make those arguments for why you don't want to test things if you do that. As opposed to, I ran half of all possible comparisons on the background seemingly at random, then you're in a more difficult position to push back against review or running 15 other ones. So if we're thinking about ordered means, the approach is going to be a little bit different than unordered means. For ordered means, what we can do is, for example, the depression example that we ran through, right? We're assuming that we're going to get some decreasing trend of depression over time across review assessments. What we can do is we can go through and start to run what we call a trend analysis. And what this is going to look at is it's going to test observe differences based on the magnitude and or in order of mean. Generally, what we see with these is you'll see a number of different trends based on sort of polynomials. So you'll see a linear trend, a quadratic trend, a cubic trend, and taking you back to, is that algebra? So basically, use your linear trend, and so the number of bends in your trend is one less than the polynomial there. So you've got a quadratic is a square, so you got one bend. You kind of got an upward or downward loop. A cubic, kind of going like this. What ends up happening is SPSS is going to run those anyway. And you might find that you have evidence for a cubic trend unless you have a good reason for expecting a cubic trend. Maybe stay away from that type of stuff. But what it's going to do is it's going to go through and we're going to say, yes, these means seem to be changing in order that generally follow some sort of polynomial function. Okay. So if honestly, this is something that you can do. I mean, sort of basically, this is just a version of a planned contrast. You could run these by hand by setting up the weights appropriately. And generally, we're wanting to use these in situations where you have equally spaced assessments. But if you have some expectation that your repeated assessment is going to follow some sort of orderly pattern or trend in terms of like linear change, quadratic change, sort of logistic change or something like that, repeated measures and probably not the test, probably not the analyses for you. In that situation, like for the depression example, you're probably going to want a growth function or an HLM or something like that is going to be a better analysis, because what that's going to be is it's going to say, yes, we're seeing changes in your outcome based on some ordered model of change, right? There's a growth function or a decay function that's predicting sort of where these things will be. Repeated measured ANOVA, you're not looking at change over time. You're looking at differences in pattern of means. Now that differences in pattern of means may correspond to an increasing trend or decreasing trend, but you're not looking at growth or change per se with this. You're looking at just, do these dots line up in a way that sort of fits a line, okay? So trend analysis is generally, you can do it. There are just better ways to do it, sort of better models for running these types of analyses. So we'll talk about trend and sort of look at sort of stuff in the output, but we're not going to spend a whole lot of time worrying about this piece of things. Okay. Where we don't see trend analysis useful is when I have my repeated measure has no meaningful order, or it does have a meaningful order, it just doesn't conform to some polynomial function, right? So I'm expecting something to go, I'm expecting a pattern, sort of like an AB design that sort of changes around, that doesn't necessarily follow a line or a quadratic or something like that. In these cases, I'm going to follow up with some planned contrast or paired sample teas to tease apart those differences. But again, wanting this to be trained into what do I think is important, what I think is relevant, what's going to give me the ability to describe the types of change that I'm seeing, or the types of differences that I'm seeing in a way that makes sense conceptually given my research question. Okay. Awesome. Okay, that's where we're going to stop. We'll jump back into when we start on Wednesday, a quick overview of our contrast, this time with a little bit of a tweak for repeated measures assessment. But we're in a good spot there. Problem set 1, due Friday. Keep working on that. Sounds like people have a good beat on those things. Let me know if you run into questions. Touch base with CJ. Otherwise, thanks. And we're on a roll this semester.